Okay, thank you so much, Mr. Chairman, for your introduction. Thank you for being here, despite yesterday nice social dinner and also the many glasses of delicious Porto wine we tasted yesterday. And so my talk will be about the use of additive manufacturing techniques in fabrication of gears. More specifically, in the fabrication of a particular type of gear sets, shown here, worm gears, basically, which have several distinct features distinguishing them from conventional gears used to transmit the motion between parallel axes. So here we transmit the motion between skewed axes, and the shape of the teeth degenerates, as you hear, in a screw and in a worm wheel, producing a very complicated contact pattern characterized by high contact pressures and by high degree of relative sliding. For these reasons, the worm wheel is currently made of bronze. Bronze is a copper alloy with a high content of copper, 90% above. But copper represents a great limitation for these gear sets, because copper was being declared by the European Commission as a critical raw material, with very severe perspective of shortage in the near future. So there is a quest for replacing, or at least reducing as much as possible, the use of copper in these components. Okay, so we have been investigating several ways of getting rid of copper. So the quest is not so recent. So here we see previous attempts we carried out in the last 10 years in cooperation with an Italian company, C-Corp, producing gear motors for elevators. And we use a test bench in our disc-on-disc rolling sliding conditions, in lubricating conditions. So we compare the conventional tribological pair constituted by quenched and tempered steel against bronze. And then we try to compare the wear rates of other different tribological pairs. So we replace the bronze with cast iron, and we replace bronze with a DLC coating on a steel substrate. So at the beginning, the results were very promising. So we were able to reduce a lot the wear rate of the tribological pair. So we tried to fabricate a prototype of gear set in which the worm wheel was made of cast iron, but the results were catastrophic in the sense that the wear rate was not the problem here. The problem was the non-acceptable level of vibration and noisiness. And so we came to the conclusion that in some way, bronze is necessary at the contact between the teeth, because bronze has a peculiar characteristic to be a solid lubricant and to have the necessary ductility to adapt itself to accommodate inevitable manufacturing and mounting errors. So we put in standby for a while the project, but after some years, I had the opportunity of organizing a workshop about additive manufacturing, and DMG Mori was present at the project, and they presented a DED hybrid machine able to deposit several coatings on substrate, including bronze. So the idea that we tried to develop with DMG Mori was to replace a bronze worm wheel with a semi-finished wheel made of cast iron or steel, in which we deposit only a thin layer of bronze on the teeth. So we started analyzing this possible solution. So as you can see here, we deposited bronze on small discs of steel. So the preliminary analysis are shown here. So they demonstrated the possibility of depositing bronze on a steel substrate. So these preliminary results have been recently published in this journal paper. But at the end, we realized that there are still some shortcomings that must be overcome. So the first one is that we, let's say, we discover a posteriori that for the sake of simplicity, DMG Mori decided to use a very small nozzle with a very small working distance and a very small nozzle diameter, with the results that the deposition rate is very small, so not compatible for fabrication processes, and the working distance is too short, so it's not able to deposit the bronze layer on the complex geometry constituted by the teeth of the worm gear. In addition, we detected porosity, and so this can be detrimental for the structural integrity of the deposit, of the coating. And you see here that the interface between the steel and the bronze layer is very sharp. And so this might be detrimental for possible delamination of the coating, of the bronze coating from the substrate. So we decided to start from scratch this project. And we involved let's say a private research center nearby Trento. ProM is the name. And they operate at DMG Mori, but have the liberty of trying the different process parameters. And so we started with them to investigate this possible coating. So here you see the powder feedstock that we use for depositing bronze. And so we started analyzing a possible combination of process parameters to identify the process windows. In particular, as you can see here, we decided to increase the nozzle diameter and enabling a larger working distance compatible with the deposition on gears. And we started exploring the effect of laser power, scanning speed, and feed rate. First, we start our tuning analyzing single tracks. So there are some very unfavorable power combinations which we found the track to be discontinuous. So we ruled out this set of parameters. And we have analyzed also the quality of the tracks in terms of dilution, so the possible diffusion of bronze into the substrate, in terms of aspect ratio of the track that must have an optimal shape to favor multiple deposition of the bronze, and in terms of porosity. And so nevertheless, the porosity was still an issue. And we discover, also based on a literature review, that also the carrier gas flow rate plays a fundamental role in the quality of the deposition made by directed energy deposition. So we started also investigating the effect of the gas carrier flow rate. And so we were able to find combinations of process parameters able to achieve a good aspect ratio, a low porosity, and the presence of dilution. So also interestingly is the fact that in some combination, as you can see here, in which we have dilution, so the interface is no longer sharp, dilution is generally accompanied by a low porosity. So we were basically interested in such process parameter combination able to achieve this double goal. Okay, so here you see let's say the results in which we interpret the quality of the tracks in terms of aspect ratio and porosity. And so we selected the process windows here, shown in green, that guarantee the best shape, the best aspect ratio, and the lowest porosity in addition to dilution. Okay, now then we move to multiple depositions. So in order to have the complete coating deposited, so the coating was deposited on pins, 4 pins on these specimens and test, and also on, say, bulky specimens mimicking the shape of a tooth. And we have developed 2 strategies. In one, the power is kept constant layer by layer, and another one in which the power is progressively decreased, taking into account in some way the fact that deposition after deposition, the temperature of the substrate increases. So here you see the cross-section of the deposits for the combination we have considered here. Again, a high value of the gas flow rate, 6 liters per minute, allows to diminish a lot the porosity and the presence of dilution. The two, let's say here, combination 2 and 4 are almost identical, even though they differ in the power modulation strategy. So at this level, it doesn't seem to play a crucial role at the necessity of modulating layer by layer the velocity power. Then we try to analyze the chemical composition gradient across the interface in 2 scenarios. In one in which we have no dilution because the gas flow rate was low, and in the second case on the right in which the gas flow rate was enough to impart dilution. So the chemical composition you see here shows a gradual transition in the bronze content in contrast to the case on the left in which we have a sudden and sharp transition in the chemical composition. Okay, then we characterize mechanically our deposits and compare the results with conventionally brought bronze. And we were able to demonstrate that basically we obtain similar hardness. And we obtain a more favorable microstructure, so a finer microstructure, much better than the classical columnar grains, dendritic grains that we observe in conventionally brought materials that you see here, the comparison. So we expect here to have a better wear rates thanks to the finer microstructure. And we perform pin on this test in dry condition. So why doing this? We want to simulate a worst scenario, typical of startup of the bore gear, in which we have a poor lubrication condition. And so we have high friction. And we wanted to, let's say, evaluate the dry friction coefficient and the possible delamination of the coating from the substrate due to poor adhesion to the interface. Okay, so the friction coefficient turned out to be comparable to that of the bronze wrought counterpart, no significant difference. And in addition, we observe no delamination of the coating from the substrate. Now we are in the process of carrying out disc-on-disc lubricated wear test, in which we are able to apply much higher contact pressures representative of in-service conditions. So with the aim of evaluating the capacity of the coating to sustain such high contact pressures. Okay, so here you see the first prototypes we have carried out. So we have turned a bar, and the bar was coated with the bronze layer, and then the bar was cut into disc for this kind of test. So here you see the main conclusions of this work that is still in progress. So I hope to be able to present more results at the next ESIAM conference, hopefully also a prototype of gear set with a deposition of bronze. And I want also to thank the financial support we obtained from the local saving banks, Caritro. Thank you so much for your attention.
Thank you very much. We have time for one quick question. We're a little bit behind schedule. Yes.
Hi, thank you for your great presentation. So copper is notoriously difficult to produce through laser because it has such high reflexivity. And I was wondering, did you try preheating the substrate at all? And also if the laser of your system is what quote unquote the red laser at 1000 nanometers or a blue or green laser?
Yes, you are absolutely right. But you need to take into account that we are not depositing pure copper. We deposit bronze that contains 10% of tin. This helps a lot to reduce the reflectivity of the powder. So I don't think that we need to change laser source in this case. In case we were depositing pure copper, then I agree with you. We should change the laser source. We have a project running now with the National Institute of Physics in Italy, in which they need to deposit pure copper. And in this case, we will opt for green laser sources. Thank you for your question.
Okay. One quick, okay.
Hi, thank you for the very interesting presentation. I have one quick question. Did you maybe try to use brass or bronze plating? For example, use a bronze as the anode and the gear as cathode and apply a current to get the thin layer on the brass or bronze on the gear teeth?
You mean a galvanic deposition?
Yes, yes.
Yes, we tried, but the delamination was an issue. So it's difficult to get a proper adhesion to the substrate in this case.
Okay, thank you.
Thank you.